Algebraic Reasoning, Chapter 1.9, Exercises 13 through 22. This section of the book has to do with cubic functions, and specifically this set here has to do with real-world type problems. There's this set here, 13 through 17, which is related to one problem, and there's 18 through 22. We're going to do this first one here, this 13 through 17. And this is a classic scenario. A box is created from a 20-inch rectangular piece of cardboard. So you have this rectangular piece of cardboard like this. I'm just going to make a little sketch to show what it looks like. So here's your rectangular piece of cardboard, and the squares of a box created, you cut out corners from each. So you take these little square corners out of each corner of this 20-inch rectangular piece of cardboard. And you create this box when you cut out these pieces by folding up these edges to form a tray or a box. So it's a classic type of problem that you'll see quite often. The squares are cut in 1-inch increments, so you can't cut 2.5 inches, so you're limited to 1-inch increments. So in this case, X, we can call X the side of each of these squares, so each of these is X. Okay. And the resulting sides folded up, taped to form a rectangular prism. So you tape these edges together. The volume of the box is a function of the side length of the square removed from each corner. The table below relates the volume of the box to the side length of the square. So now we go to the table, and the table is going to be a cubic relation. In fact, it says problem 13, generate a cubic function model for the volume of a tray when given the side length of the square cut from each of the corners. So we go through the same process we've done in the past. We take first differences. So we take 396 minus 0, so that's going to be plus 396. We definitely want to get our little calculator for this one. We have 640 minus 396. So we get 244. Then we have 756 minus 640. Actually, that's going to be 116. Then we have 768 minus 256. That's going to be plus 12. Then we have 700 minus 768, which could be negative 68. Then we have 576 minus 700, which is going to be negative 124. Then we have 420 minus 576. That's going to be minus 156. We have 256 minus 420. So back to the calculator. So we get negative 164 for that. Is that right? 256 minus 420. Yeah. It's going to be negative 164. $108 minus 256. that we get negative 148. Okay, the second difference is we have 244 minus 396. We get negative 152. Then we have 116 minus 244. Get negative 128. Then we have 12 minus 116. That's going to be minus 104. We have negative 68 minus 12. That's going to be negative 80. We have negative 124 minus negative 68. So that's going to be negative 124 plus 68. That's going to be negative 56. Then we have negative 156 minus negative 124. So that's going to be the same as negative 156 plus 124. For that, we get a negative 32. Then we get a negative 164 minus negative 156. So that's going to be the same as negative 164 plus 156. That's going to be negative 8. And then we have 148 minus negative 164. That's going to be the same as negative 148 plus 164. It's going to be plus 16. Okay, so those will be our second differences. And now we get to our third differences, which is going to determine our A value here. So we have negative 128 minus negative 152. So that's going to be plus 24. We have negative 104 minus negative 128, so that's going to be plus 24. And negative 80 minus negative 104 plus 24. So we see where we're going, right? Negative 56 minus negative 80 is going to be plus 24. And we are going to go plus 24 all the way down here for our third difference. So third difference is equal to 24. Well, already in the f of x equals ax cubed plus bx squared plus cx plus d. There we go. Get this thing back. Plus d. Not too terribly legible. Anyway, already we know we have a y-intercept of 0. So we have c is equal to 0. We have our third difference is equal to 24. So in the equation, Q equation, third difference is equal to 6a. So 24 is equal to 6a. So we divide by 6. We have a is equal to 4. So I put up here a is equal to 4. Now next, the first second difference, as we go from 0 to 1, we get negative 152. So, okay, so first second difference is equal to 6a plus 2b. And for that, we have negative 152 is equal to 6a, and 6a we already determined to be 24 plus 2b. Well, subtracting 24, we get negative 176 is equal to 2b. And dividing by 2, we get b is equal to negative 88. So I'll put up here b is equal to negative 88. And the last thing we're going to look at is our first difference is equal to a plus b plus c. So our first difference is 396. It's equal to a, and a is equal to 4 plus b plus c. So we get minus 88 plus c. So those should be equal. So we have 4 minus 88 on the right side. I'm going to bring down this 396. 4 minus 88 is going to be negative 84 plus c. If we add 84, we should get 396 plus 84. That's going to be 480 is equal to c. So I'm going to put up here c is equal to 480. So we have all the components now, and so our function I'm going to write in this little space here. We have f of x. It says y, right? It says y in the table. So y equals ax squared. So that's going to be ax cubed. So 4x cubed. And we have b is negative 88. So we have minus 88 x squared plus cx, and c is determined to be 480. So plus 480 x. And c is, d is 0, we determined. So this is going to be our function or model right here. Okay, next we go to problem 14. What side length of the square produces a tray with the greatest volume? Well, here's the volume. Okay, now these are all integers, but we look at our choices available to us, and our biggest volume is created by this x equals 4. So we'll say when x is equal to 4. Now, I happen to work this out using calculus and figured out this, the real value, the optimal value of x is going to be a little less than 4, but they left us with just the integer options over here on the left side as possibilities. Okay, next, 15. The graph below represents the data in the table and the function that models the table. What is the domain and range of the situation? Well, the domain we were given as the input values, right? So domain is going to be simply, we could say x equals, let me go ahead and do that. Let's say x equals, I'm going to put kind of in set notation here, We have 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9, right? Is that all we're given? I think so, right? Okay, so that'd be our domain. So our range is going to be the corresponding y values. So we'll say y is equal to, I'm going to put this notation here. Now, for this one, the y values are simply the values in the table. So we put in 0, comma, 396, comma, 640. I'm going to bring this over to 640, comma, 756, 768, comma, 700, comma, 576, comma, 420, comma, 256, comma, 108. So that would be our domain and range for this situation. Okay, number 16. The graph below represents the data in the table and the function that models the data. Models a table, but has been graphed with a different window setting. Why are there no individual points plotted on the graph for x is less than 0 and x is greater than 10? Okay, here's x is 10 over here. No, that's not it. Here's x is 10, right? So x equals 10. And over here we have x equals 0. Well, why do we only go between 0 and 10? X equals 0 and equals 10. Well, 0 is obvious. We can't cut a negative distance, right? I'll say not less than 0 because we cannot have x be a negative distance, right? We cannot have negative, so I'll just put it like that. And why not greater than 10? Well, it's pretty much for the same reason. And when you consider the drawing of the box initially, we wouldn't have enough room to work with. So there are different ways of saying it. So we'll say not greater than 10 because we don't have enough box length for bigger, right? Box, not box, but cardboard length. Cardboard length limits us. I guess that's a way to say it. Okay, and then 17. Why does the domain and range only contain whole numbers? Well, here we just go back to our initial problem, and we're cutting in 1-inch increments, right? So the conditions only allow for 1-inch increments. So we just put the conditions allow only for 1-inch increments. Okay, so that would be that. Now, I think that's the exercise set I'm going to work on in the video lesson. If you go on to numbers 18 through 22, it's a different problem set that is a kind of a comprehensive problem, and it's this soccer ball type problem. So you have the same type of analysis that we had in problems 13 through 17 that we just went through. Well, good luck on this and on all your other problems, and thanks for viewing.